Welcome to today's paper reading. Today's paper is titled, PDiscoFormer, Relaxing Part Discovery Constraints with Vision Transformers. This paper was published on AR14 by Ananthu, Aniraj and colleagues from INRIA and INRI. The abstract highlights the development of computer vision methods that explicitly detect object parts, aiming for more interpretable models. Existing approaches often make restrictive assumptions about the geometric properties of discovered parts, such as being small and compact. In contrast, this paper demonstrates that pre-trained transformer-based vision models, like the DINOv2 ViT, can relax these constraints. Specifically, the use of a total variation (TVE) prior, which allows for multiple connected components of any size, significantly outperforms previous methods. The approach is tested on 3 fine-grained classification benchmarks: CUB, PartImageNet, and Oxford Flowers. The results show substantial improvements in both part discovery metrics and the downstream classification task, indicating that the strong inductive biases in self-supervised ViT models necessitate a reevaluation of the geometric priors used for unsupervised part discovery. Deep neural networks, particularly convolutional neural networks, CNNs, and more recently vision transformers, ViT, have significantly advanced the field of computer vision. However, the black box nature of these models often restricts their application in domains requiring interpretability. Post hoc interpretability methods, such as generating saliency maps, are commonly used to understand the internal processes of these models, but these are approximations and can be misleading. Recent efforts have focused on developing interpretable by design deep neural networks, aiming to identify semantically interpretable features. Despite these advancements, balancing interpretability with performance remains a challenge, especially when generalizing part shape priors across different datasets and tasks. Figure 1 illustrates the contrast between concentration and total variation as part priors in computer vision models. The concentration prior assumes parts to be small and compact, which is restrictive but useful in specific scenarios. In contrast, the total variation prior allows for parts to consist of multiple connected components of any size, providing a more flexible approach. This figure highlights the performance differences on fine-grained classification tasks, showing that the total variation prior, when combined with appropriate losses, can substantially outperform methods relying on concentration priors. In unsupervised part discovery, the goal is to identify a small number of semantically consistent parts, typically around k equals 8, that are shared among classes in a dataset. These parts are visualized through per-part saliency maps, which facilitate easier interpretation. However, this task often relies on assumptions about the distribution and shape of the parts. For instance, some methods assume that parts follow a beta distribution or are present at least once in a mini-batch. Additionally, assumptions about part shape, such as imposing a spatial Gaussian prior, can be restrictive and may not generalize well. To address these limitations, our proposed method avoids such shape priors and only enforces that discovered parts should form connected components. Figure 2 illustrates the PDiscoFormer architecture designed for part discovery. This architecture builds upon previous methods by relaxing the constraining concentration-based part prior with a more flexible total variation prior. The key innovation lies in the combination of an entropy loss and Gumbel softmax on the part maps, which allows for consistent and high-quality part maps. This approach makes better use of the representation of self-supervised pre-trained vision transformer (ViT) models and is applicable to tasks with diverse types of parts. The architecture is capable of localizing up to a fixed number of semantically consistent parts of an object without relying on part annotations, using only classification labels as supervision signals. The model architecture begins with an image X in the dataset, represented as a tensor. A backbone model H theta is used to extract a feature tensor Z. Attention maps A are computed to identify semantically interpretable image regions. The model employs several loss functions to guide the learning process. The classification loss ensures the discriminative nature of discovered parts. The orthogonality loss encourages distinct part embedding vectors. The equivariance loss ensures part detection remains consistent under transformations. The approach does not assume any specific part shapes or sizes, relying instead on weakly supervised learning to uncover discriminative parts. The experimental setup involves the use of 3 primary datasets: the CUB dataset, which includes images of 200 bird species, the Part ImageNet dataset, comprising 158 classes distributed among 11 superclasses, and the Oxford 102 flower dataset, which contains 102 flower classes. All models were implemented using the PyTorch framework, starting with the DINOv2 ViT model and utilizing register tokens. Evaluation metrics include keypoint regression for the CUB dataset, and normalized mutual information, NMI, and adjusted RAND index, ARI, for assessing clustering quality across datasets. Table 1 presents a quantitative comparison of the part discovery and classification capabilities of our model against related approaches from the literature. The table includes datasets such as CUB, flowers, and Part ImageNet OD, with metrics like NMI, ARI, Top 1 accuracy, and FG, MIU. The number of parts, denoted as K, is a key variable in the comparison. Our model consistently outperforms existing approaches across all datasets, demonstrating superior performance in both part discovery and image classification tasks. In the quantitative analysis, our model consistently outperforms existing methods for both part discovery and image classification across various datasets. This is particularly evident in significant performance gains observed on the flowers and Part ImageNet datasets. Our model maintains robust accuracy even as part complexity increases. The qualitative analysis showcases our model's ability to accurately discover irregularly shaped body parts and achieve tighter coverage of object boundaries. This is especially notable in parts that are relatively large. The ablation study highlights the impact of individual loss functions and architectural elements, demonstrating the overall effectiveness of our approach. Figure 3 presents qualitative results on the CUB dataset for K equals 8. This figure compares the performance of our model, PDiscoFormer, with the state-of-the-art PDiscoNet. The results demonstrate significant performance improvements, particularly in maintaining robust accuracy for any number of parts. Our model consistently outperforms existing approaches for both part discovery and image classification across all datasets, attributed to the synergistic effects of the strong inductive biases ingrained in the self-supervised ViT backbone and the enhanced flexibility of the proposed combination of geometric priors. Figure 4 presents qualitative results on the Part ImageNet dataset for K equals 8, highlighting the model's ability to accurately discover irregularly shaped body parts. This includes parts such as bird wings, flower petals, and the body of a snake. The figure underscores the importance of geometric part priors that favor piecewise constant and spatially connected components. It also showcases the model's improved consistency and semantic interpretability of parts, as evidenced by the clear identification of parts like snouts and ears in quadruped images, which contrasts with the less clear parts discovered by competing methods. Figure 5 presents qualitative results on the flowers dataset for K equals 2. This figure highlights the performance of our model in detecting the foreground and classifying the flowers, regardless of the number of parts. It also contrasts our approach with PDiscoNet plus ViTB, showing that our model excels in both classification accuracy and foreground localization, while PDiscoNet plus ViTB struggles with the latter. Figure 6 illustrates the effect of varying the number of parts, K, on the performance of PDiscoFormer across different datasets. On the left, we see the flowers dataset with K values of 2, 4, and 8. The middle section displays the CUB dataset with K set to 4, 8, and 16. Finally, the right side shows the Part ImageNet dataset with K values of 8, 25, and 50. This figure helps to visualize how the granularity of part discovery changes with different K values, demonstrating the model's adaptability to various datasets and part complexities. Figure 7 presents qualitative results from the ablation study, highlighting the impact of various loss functions and architectural elements on part discovery. Total variation, LTV, effectively prevents spurious part activations in the background, which is crucial for maintaining the integrity of foreground parts. The absence of background loss, LP0, results in the model incorrectly treating the background as a foreground part, demonstrating the necessity of this loss function. Presence loss, LP, and part dropout are shown to promote the use of all parts, preventing the dominance of a few parts and ensuring a balanced part discovery process. These findings underscore the importance of each component in achieving consistent and accurate part discovery. Table 2 presents the results of an ablation study conducted on the PDIMageNet and CUB datasets. The study evaluates various model configurations by measuring their performance in terms of top 1 accuracy, ACC, normalized mutual information, NMI, adjusted RAND index, ARI, and KP, part level compactness. The table highlights the impact of removing specific components such as layer norm, no per part layer norm, dropout mechanisms, no part dropout, no gumble, and different loss functions, no LP0, no lent, no LEC, no LUPTAC, no LP1, no LTV. The results indicate that the full model outperforms its ablated versions, demonstrating the importance of each component in achieving high accuracy and interpretability in part discovery tasks. The study was limited to datasets with part annotations and FGBG masks for the test set, enabling quantitative comparison with state-of-the-art methods. Future work could explore training the model on larger and more diverse datasets, which may introduce more variability in object appearances and poses, challenging the model to generalize better. Additionally, methods to automatically estimate the hyperparameter K, the number of parts to discover, could enhance the model's adaptability and streamline the training process. Integrating the method with unsupervised object discovery research could enable part discovery within each detected object, improving capabilities in complex scenes. In this paper, the authors introduced PDiscoFormer, a novel approach for unsupervised part discovery. Unlike previous methods, PDiscoFormer, based on self-supervised vision transformers, relaxes strict geometric priors. This model leverages a total variation prior to achieve significant improvements in part discovery and downstream classification accuracy, outperforming state-of-the-art methods on datasets such as CUB, PDIMageNet, and Oxford Flowers. The study emphasizes the importance of rethinking geometric priors in part discovery, especially for objects with complex shapes or multiple occurrences within the same image. By avoiding specific shape or size priors, PDiscoFormer demonstrates enhanced generalization capabilities, making it suitable for a wider range of fine-grained image classification tasks. The strong inductive biases learned by vision transformers during self-supervised pre-training enable the use of flexible shape priors like total variation, resulting in robust performance across all tested datasets. Thank you for watching.